Omar and I will be presenting about vibration absorbers. So, vibration is a mechanical phenomenon which involves oscillations occurring about an equilibrium point. Let me first explain what the two types of vibrations are. The first one is forced vibration, which occurs due to external disturbances in the system. For example, the string of the guitar, as shown in this video, is forced to vibrate, causing a set of waves to generate, while free vibration occurs when an initial force is applied to the system and then the system vibrates freely. This video shows how a free vibration occurs in a pendulum. So, in a pendulum, only a simple push can leave the pendulum swinging by itself and producing waves. Vibration in vehicles and structures. Vibration in vehicles and structures need to be reduced for several reasons, which introduced the need for vibration absorbers. A spring is the simplest kind of vibration absorber whose design helps in reducing vibration in a system. For our project, we had to choose the best material for the spring in order for it to be used as a vibration absorber in structures and buildings. The requirement for choosing the material were high ductility and tough and strong materials. The options we had for the material included music wire, oil-tempered wire, hard-drawn wire, chrome vanadium, and chrome silicon. After examination of all the materials and a lot of hard work, we ended up choosing chrome silicon because it has a long life, it is good for high stress conditions, and can also be subjected to shock loading. Other than that, it had the highest hardness level, which translates to high strength. Torsional and shear stress are the two stresses applied on the spring system.
Hello, my name is Omar Ahmed, and today I'm going to present about the TMD, which is also known as tune mass damping. Even though we have mastered in this, we haven't mastered in this topic. We have been exposed to certain ideas after thorough research. So, first thing, what is tune mass damping? A tune mass damping is a device mounted in the structure to reduce the unwanted amplitude of the mechanical vibration. This TMD mechanism can be utilized to prevent damage, discomfort, or of severe structural failure. TMD application has been widely applied to power transmission, automobiles, industry, and buildings, etc. Sometimes TMD is also known as harmonic absorber. So I'm going to explain about the basic working where it's utilized in the power station, in the mechanical industry, in the Taipei Tower, which is one of the famous tower, as well as in Burj Khalifa. It has 6 dampers right now, as well as on the bridge suspension. So let me describe about the governing principle of this mechanism. M1 over here, it acts as an important component. It can be either machinery or building, etc. M1 vibrates due to operation of operation or sudden shock created by external force, which acts on the spring K1 and damper C1. After a force of Fo is in order to reduce the force, external force acted on it, M2 is attached to M1 with the help of a spring K2 and a damper C2. The second mass M2 acts as a counter oscillator. Fo force is a force on M1 which acts as external force, for example earthquake. The energy transferred from M1 to M2 is dissipated through the loss of energy in the form of heat through a damper. So we came across some of the complicated equation of TMD, but we have still managed to understand the basic equations such as this one. It's the formula for harmonic motion, but we haven't gone into depth to the extent to understand the complete usage of this equation. And this is also one of the famous equation. It's used for the pendulum for the suspended mass. And one of the most famous one is of this one, which is used for the buildings, bridges, etc. And there is no involvement of mass. So I'm going to show a video which is one of the best in the States. It's a LAX observation deck in Los Angeles. The engineers wanted to build a unique structure, and the challenges to use less building steels was one of the big thing because it would ruin the structure view of the building. So I'm going to skip here and
There are a lot of people saying
earthquake protection technology to in applying modern earthquake protection technology to an historic building while not changing the way it looks.
you cannot do anything to that structure, but somehow make it better. That's a challenge.
A non-creative engineer would have just put more concrete and steel on the outside of the building and made it stronger.
It would ruin its appearance. It would be very costly and very time-consuming. Would not have been the theme building any longer.
That's really what led to using a tune mass damper.
The unique solution is to take 1.2 million pounds of steel and put it on top of the building. Normally in earthquake engineering, that's stupid.
As an engineer, you're always taught that the more weight you put on the building, the worse it is. And then when our consultants tell us we want to add 20% of the weight of the building and stick it on the very top, but are you guys serious?
The idea really came to us from Kit. It was an unusual idea, but once he proposed the idea to us, it suddenly sounded right.
The way I describe the tune mass damper is we put 1.2 million pounds on 8 rubber bearings. DIS manufactured the rubber bearings. The rubber bearings help control the movement of the 1.2 million pounds. Then there's 8 shock absorbers, or fluid viscous dampers, made by Taylor Devices. As the tune mass damper moves, those 8 shock absorbers absorb the energy of that movement. The 1.2 million pounds counteracts the earthquake motion.
It acts as a counterweight. So if this building want to shake that direction, the whole mass go in the other direction to dissipate the energy down there.
So the ground is trying to shake the building, and the building moves at a particular frequency, and you make sure that at the same frequency you have a mass that opposes the building as it tries to move back and forth. You hold it back.
We're trying to modify the structure's behavior, make the mass move during an earthquake and the building move a lot less.
So the